Good morning everyone. Today we are going to see about Gauss law and its applications. So basically the Gauss law is used to find the electric flux density or electric field intensity. So before going deep into the Gauss law and its applications, let us first know some of the fundamentals. The first thing that we have to know is what is flux, and the next one is what is electric flux density. So consider two charges are there, plus q and minus q. So when these two charges are kept at a certain distance, then there exists some force between these two charges. So it is nothing but the electric lines of force that exist between these two charges. So the number of lines which is present from one charge to the another charge is known as the electric flux. So the electric flux is denoted by the term xi. So here these lines of forces are never intersect each other, and these lines of forces are parallel to each other. So consider this negative charge doesn't exist, then the lines, the electric field lines that comes from the positive charge will end at infinity. So similarly, if there is a negative charge, then the negative charge will have electric fields of lines inwards towards the charges. So this is about the electric flux. And then coming next to the electric flux density, consider a same two charges plus q and minus q exist. So here we will have field of lines that moves from positive charge to the negative charge. So here consider a surface charge ds along the lines of force. So consider this as a unit surface. So the number of electric flux to the unit surface area gives our electric flux density. So expressing this electric flux density in a vector form, we shall write d vector is equal to d xi by ds. So this is our vector form of the electric flux density. And then coming next to the Gauss law and its applications, consider in a three-dimensional axis x, y and then z, we are having a sphere which has radius r. So let us assume a charge which is present in the origin. So here because of this charge q, we will have electric flux density that is normal to the Gaussian surface. So here we will have electric flux density in all the axes, existing in all the axes. So this electric flux density, it will be either normal to this surface or it can be tangential to the surface. So if it is normal to the surface, then the Gauss law can be applied. Suppose if it is tangential to the surface, then our value of d dot ds will be equal to 0. If it is normal, then the value will be d dot ds for the vector d vector dot ds vector. So this can be a point charge or it can be a line charge that exists in this three-dimensional axis. It can also be a line charge. So whatever may be the charge distribution that is there inside the sphere, it should enclose. That is, the charges which is present on the in the three-dimensional axis, it should enclose the surface. And then next is the Faraday's law was one which was extended into the Gauss law. So the Gauss law states that the net flux enclosed by the closed surface will be equal to the charge enclosed by the surface. So which means that the number of charges which is present inside the surface will be equal to the flux which is there. Okay. So xi is equal to q enclosed. So this can be written as xi is equal to q enclosed, which is equal to closed integral of d dot ds vector. So let us see how this closed surface integral of d vector dot ds vector exists. So from the Gauss law, from the electric flux density, we shall write d xi is equal to d dot ds. Here this d denotes the magnitude of the electric flux density. So this magnitude of the electric flux density can be written as modulus of electric flux density vector into cos theta. So this theta is the angle that exists between our electric flux density to the surface. So substituting this equation in this one, we will get d xi is equal to modulus of d vector into cos theta into ds. So we know that the dot product of two vectors a vector dot b vector will be equal to modulus of a vector modulus of b vector into cos theta. So this is of the form modulus of a vector into modulus of b vector into cos theta. So it can be written as d xi is equal to d vector dot ds vector. So if we are taking integration on both the sides, then we will get integral of d xi is equal to integral of d vector dot ds vector. So here when we see the Gauss law is applicable only for the closed surface. So this is a closed surface integral. So the integration where the surface where the integration applied is known as the Gaussian surface. So while we are considering the Gaussian surface, it is an imaginary surface where the d vector should be normal to the surface or it should be tangential to the surface. So along the Gaussian surface, the d vector will be constant throughout the surface. So from this we shall write xi is equal to closed surface integral of d vector dot ds vector. So this is for the assumption what we have done. So next is, suppose we are having a number of charges q1, q2, q3, q4 up to qn that exist in a particular surface. Consider this as a surface. So here we are having a number of charges. So in this case the xi will be equal to q, which is equal to the summation of all the charges qn. Similarly, if you are having a line charge, then considering it has line charge density of rho l, then xi will be equal to q, which is equal to integral of rho l into dl. Similarly, we can write for surface charge integral as well as for the volume charge integrals. Consider there is a surface like this, then for this the Gauss law can be written as xi is equal to q, which is equal to surface integral of rho s into ds. Similarly, if you are having a volume like a sphere or a rectangle or a square, then for that we shall write, xi is equal to q, which is equal to volume integral of rho v into dv. So as a final we shall say that the surface should enclose whatever may be the charge that is present. So suppose whatever may be, if it is a charge, then it should be enclosed in a surface. So this surface is nothing but the Gaussian surface. If it is a line charge, it should be enclosed by the surface. If it is an area, then it should be enclosed by the Gaussian surface. If it is a volume, then it should also be enclosed by our surface. So these surfaces are nothing but the Gaussian surface. So the charges or any type of charge distribution, it should be enclosed by the Gaussian surface. The charges which are present outside of these surfaces cannot contribute to the electric flux density of the charges which is present inside the surface. So if there is any charges that is present outside of the surface, then it cannot contribute and it should be neglected. And I will give you another example. Consider a volume V1 which has charge 10 nanocoulomb and minus 2 nanocoulomb which is present inside this volume. and we are having another charge 20 nanocoulomb that is present outside of this volume. So here the total charge which will contribute is 10 nanocoulomb minus 2 nanocoulomb, which is equal to 8 nanocoulomb. So this 20 nanocoulomb will not have any effect over the electric flux density which is existing for this volume V1. Similarly, consider another volume V2 which do not have any charges, but outside of this volume V2 we are having 5 nanocoulomb. So for this there will not be any charges, it does not have any charges, so electric flux will be equal to 0. So this is one of the cases. So whatever may be the charges that is present outside of a volume or a surface, it will not contribute to the electric flux density. So next we shall apply the Gauss law to a point charge which is present in a 3-dimensional axis. Consider a 3-dimensional axis x, y and then z. So it has a point charge q in the origin. So the electric flux density will exist in all the 360 degrees. So we are going to measure electric flux density at point P. So if this is a positive charge, then we will have electric flux density which flows outside of this surface. So this is our electric flux density. So see here, this is the Gaussian surface that we have considered. So this electric flux density, it is normal to this Gaussian surface. So here let us write Gauss law, xi is equal to closed integral of d dot ds vector. So here, since it is normal, then the integral will be changed as d dot ds. So here this is a spherical coordinate system, we have to consider spherical coordinate system in order to evaluate our xi. So if you are considering a spherical coordinate system, then ds will be equal to r square sin theta d theta and then d phi. So why we are considering this differential surface area means, this differential surface area formula, it is along the AR vector. So if this is our radius r that exists between origin to the point P, then our electric flux density is along the radius. So we will have unit vector AR vector which is along our radius. So we will have this formula. So applying this formula to this equation, we shall have xi is equal to surface integral of d dot r square sin theta d theta d phi. So if it is a surface integral, then we know that it is a double integral. So xi will be equal to double integral of r square sin theta d theta d phi. So here one integral will be applicable for theta. So theta in case of spherical coordinate system, it always varies from 0 to pi, whereas phi will varies from 0 to 2 pi. So integrating, we will get so now we have to integrate this surface integral. So xi will be equal to, if it is a surface integral, we know that it is a double integral. So one integral exists for phi. So this phi will varies from 0 to 2 pi, and then another one integral is for theta. So theta exists from 0 to pi d r square sin theta d theta and d phi. So here d and r square are constant, so we are taking it outside. So d r square double integral of phi is equal to 0 to 2 pi, and then if you are integrating this one, So upon integrating, psi will be equal to, taking d and r square outside since it is a constant, so dr square into double integral. So if you are integrating, then we will get the value of 4 pi. So d can be written as psi divided by 4 pi r square. So this is the magnitude of the electric flux density what we have obtained. So writing it in a vector form, we shall write d vector is equal to psi by 4 pi r square into ar vector. So this indicates that d vector has a magnitude psi divided by 4 pi r square, where 4 pi r square is the surface area into ar vector. So ar vector denotes the direction of our electric flux density. So again coming back to this diagram, we shall see that the charge which is there in the origin. So our electric flux density, it has direction along the radius r, and here the d vector, it is normal to our Gaussian surface. So our Gauss law can be applied only if electric flux density is normal to our Gaussian surface. We shall see another one example for the line charge. So let us consider a line charge that exists along the 3-dimensional axis x, y and then z. Let the line charge, we shall keep it along the z axis from the origin. So let us assume the length of the line charge be small l. So while we are applying the Gauss law, psi will be equal to integral of d dot ds vector. So when we take a line charge, from the line charge the electric flux will be coming outwards. So if it is coming outwards, then we will have electric flux density that is coming outwards in all the 360 degrees. So if it is coming along the 360 degrees, then we have to consider a cylindrical coordinate system in order to evaluate it. Let us evaluate the electric flux density at the point P. Let the radius from the z axis or from the line charge to the point P, let it be a small r. So from this we shall know that our electric flux density direction is along the radius r. So it is ar vector, and here we are having the electric flux density d vector. So this can be written as psi is equal to closed surface integral of d vector into, so for this ds vector we have to consider the cylindrical coordinate system. So ds vector along the unit direction ar vector, the formula is r. So this is a ar vector. So we will have d phi dz into ar vector. So this is our equation. So here we are going to consider only the magnitude, because the cylindrical surface what you have considered, it is a Gaussian surface. Here the electric flux density, it is normal to our Gaussian surface. So we shall write this surface integral as d dot ds. So here psi will be equal to surface integral of d dot, instead of this ds you have to substitute the value d dot r d phi dz. So we know that surface integral is a double integral. So while we are integrating it, we will get the equations like psi will be equal to d, and then there r is also constant, and then we have to integrate it. So if it is a surface integral, then we will get two integrals. So phi varies from 0 to 2 pi, and then for the z it is 0 to z, we shall write 0 to z. But we are having a line charge which has length L, so it is very finite. So we shall write z exists from 0 to small l. So we will have d phi and then dz. So psi is equal to d into r. Upon integrating, we will get phi that varies from 0 to 2 pi, and z will varies from 0 to l. So we will get the equation d into r into 2 pi into l. So from this we shall write d is equal to psi divided by 2 pi r into l. So this is the magnitude of the electric flux density for our line charge that exists on the z axis which has length L. So writing this electric flux density in the vector form, d vector is equal to xi divided by 2 pi RL into AR vector. So as I have told earlier, xi by 2 pi RL indicates the magnitude of the electric flux density and AR indicates the direction of our electric flux density. So here also our electric flux density, it is normal to the Gaussian surface, which is here it is a cylindrical surface. So this is our equation that is obtained from the Gauss law. So we shall also get the similar equation from the Coulomb's law also. So what is the difference between the Coulomb's law and the Gauss law is that Coulomb's law, it is applicable for both symmetrical charge distributions as well as for the non-symmetrical charge distributions, whereas the Gauss law, it is applicable only for the symmetrical charge distributions. So here we have got the electric flux density. So from this we can get the electric field intensity also. So the relationship that exists between electric flux density and electric field intensity is d vector is equal to epsilon into E, where epsilon is the permittivity. So here permittivity is given by epsilon naught into epsilon r. Epsilon naught is the permittivity of the free space and epsilon r is the relative permittivity. So here our line charge, it is there in the free space. So epsilon r value will be equal to 1. So the d vector will be equal to epsilon naught into E vector. So here we have got d vector equation. We shall write that xi divided by 2 pi RL into AR vector, which is equal to epsilon into E vector. So from this we shall write E vector is equal to xi divided by epsilon naught 2 pi RL into AR vector. So this is the equation that we have obtained from the Coulomb's law for the line charge. So both are same, but the difference between Coulomb's law and Gauss law, as I told earlier, it is Gauss law is applicable for the symmetrical charge distributions, whereas Coulomb's law is applicable for any type of charge distributions. So let us see in another one example that has a surface. So for the surface charge, let us determine the electric field flux density. So consider 3-dimensional axis x, y and then z. Consider a surface along in the xy plane where z is equal to 0. So here consider a small surface along this sheet of charge. So here the surface charge density of this infinite sheet of charge where it is placed is rho s. So we are going to find electric flux density along this small surface ds. So here the electric flux density will be flowing upward from this surface and then it will be flowing downwards from this surface. So our Gaussian surface will be like this. So this is how our Gaussian surface will be there for this surface charge. So here applying Gauss law, psi will be equal to closed surface integral of d vector dot ds vector. So here an interesting thing is there, the electric flux density will be there in the top surface, we may have in the bottom surface and we may have in the side surface of this Gaussian surface. So we are going to write this equation as top surface integral of d vector dot ds vector plus bottom surface integral of d vector dot ds vector plus side integral of d vector dot ds vector. So this is our surface that we have considered. So electric flux density will be flowing upward and it will be flowing downward. So, we will have electric flux density along the top surface and the bottom surface, whereas we will not have electric flux density along the side surfaces. So, here this integral it will become 0. So, this equation become xi is equal to top surface integral of d vector dot ds vector plus bottom surface integral of d vector dot ds vector. Suppose consider this area as capital A. So, if this area has a capital A, then the bottom surface will also have area capital A. So, xi will be equal to d vector closed integral of we have ds vector. So, we shall write this as A plus d vector. So, both the areas are same. So, we shall write this as also as capital A. So, xi will be equal to d vector into 2A we will be having. So, here the sheet of charge what you have considered has a surface charge density rho s. So, it can be written as xi is equal to q is equal to surface integral of rho s into ds. Here we have seen that integral of ds, that is the area, is actually capital A. Similarly, here also we will have capital A. So, q will be equal to rho s into A. So, this both these equations are, we can equate this, both these equations, consider this as 1, let this be 2. So, comparing both these equations, we shall write d vector 2A is equal to rho s A. So, from this A will get cancelled. So, we shall write d vector is equal to rho s by 2. So, and then it is along the direction, which is normal to our Gaussian surface. So, we shall write an vector as common. So, this is about our surface charge. So, the Gaussian surface what we are considering plays a very important role in our Gauss law. So, the Gauss law can be applied only for the Gaussian surface. So, this Gaussian surface it should be normal to our electric flux density, and then the Gaussian surface what we are considering it should enclose the charges. So, the charges can be a point charge, line charge, surface charge, it can also be a volume charge. So, thank you.